Hello everyone, can everyone hear me? I'll take the smiles as a yes. So my name is Daniel LeBlond. I'm a senior project engineer at Metro Vancouver, and I'm here with Iran to present on the Iona Island Wastewater Treatment Plant projects, specifically on our geotechnical program. I just want to start off this presentation in a good way and just, hold on a sec here. I'd like to acknowledge that we're gathered today in the traditional, ancestral, and unceded territories of the Coast Salish peoples, including the territories of Musqueam, Squamish, and Tsleil-Waututh people. Our project, the Iona Island Wastewater Treatment Plant projects, are located on Musqueam's core territory across the north arm of the Fraser River from their primary reserve. Metro Vancouver has been working collaboratively with Musqueam on these projects and will continue to be doing so as we improve the water quality and the treatment process at the Iona plant. So I just want to talk about what our project is, and then I'm going to pass it over to Iran to talk about some of the more relevant details for this audience, for our geotechnical program. But essentially, the existing wastewater treatment plant at Iona was built in the 1960s. It was built to a primary level of treatment only, which is kind of the bare minimum when it comes to wastewater treatment. There's been some regulation changes that have required us to upgrade this to at least secondary treatment. They're both from the provincial and the federal government. And we have been given a regulatory mandate as Metro Vancouver, the regional district, once known as the Greater Vancouver Regional District, to upgrade this plant by 2030. So a lot of things to work on there. So where is Iona? The Iona Island Wastewater Treatment Plant is just north of Sea Island or the Vancouver Airport. You can see the area in pink on the screen here is the Vancouver Sewerage Area, and this is all the homes and buildings and services that contribute sewage to this wastewater treatment plant. We are building it to accommodate for growth up to about just under 1 million people by 2051. And one interesting thing to note about the Vancouver Sewerage Area, it is a combined sewer system, and that means we get both stormwater and sewage from municipal sources. And that makes the design of the plant quite challenging because the flows are quite variable depending on what the weather conditions are. So if we have a heavy rain event, the flows and the concentrations of contaminants are quite a bit different than if we have a sunny day. So it makes the things a little bit more challenging. But that's why we're here. So I'm not going to go too far into wastewater treatment. That's not my area of background. That's not for this audience. But I just want to kind of highlight a little bit what we're looking at here. So the existing plant is not shown too well here. We're looking to build, kind of a primary treatment, secondary treatment, and also tertiary treatment elements. We're also looking at doing resource recovery, which includes renewable natural gas, reclaimed water, and also reclaimed heat from the effluent. There's actually, the sewage that comes to us contains a lot of heat, and there's ways to actually pull that heat out and use it in a good way. So we're looking to build some of those opportunities as well. This is what we got from our architects. It's kind of a nice rendering of what this is going to look like on the island. So it's a fairly expansive upgrade. So this, just to orientate ourselves, this is looking towards the west, so towards the Salish Sea, on the right hand side of our image here. So I guess I can go corner. Yeah, so down here would be YVR. Over here on this side would be kind of South Vancouver, and we're looking out towards Vancouver Island. So if you haven't been to Iona Island, I will say this is our plug for the park. It's a very nice park. We had about 280,000 visitors per year. And as part of this project, we are planning a whole suite of other upgrades to other areas of the ecosystem. So just kind of looking at some of the other priorities outside of just wastewater treatment, we have some other clear ecological priorities for our project. Fostering resilience to sea level rise is something that's actually incorporated into our geotechnical design. We'll talk a little bit more about that in a little bit. But essentially, we've decided as a core of the project, rather than to build a berm or a dike around the existing site, we're actually going to increase the elevation of the entire site to a new flood construction level. And that increases at this point roughly around 3 meters in elevation increase. So it's a fair amount of change to the island. We are looking to connect people with nature, and that's to kind of integrate both the plant and expand some of the access to the park that the public has. As I said at the beginning of the presentation, that we are looking to collaborate with Musqueam and insert some of their traditional knowledge and values into the design and the execution of our projects. We're also looking to restore estuary and fish habitat. There's a number of projects to create new off-channel streams and habitat for fish, and also to improve fresh and saltwater mixing and conductivity. We're also looking to enhance terrestrial and freshwater habitats, and also, the core of the whole program is to improve water quality, which is the improved treatment at the wastewater treatment plant. So this is just kind of a graphic showing kind of some of the ecological projects we have planned. So we've got a mixture of terrestrial, aquatic, nature-based adaptations, and freshwater restoration projects. It's a fairly large, comprehensive set of ecological upgrades. And I believe it will be the largest kind of, single collection of ecological upgrades from a single project in at least Western Canada, if not Canada. So it's a fairly large undertaking in itself. And something we're quite proud of to display, as yes, we're building a treatment plant, but that's not the only piece of the work. So just to talk a little bit about where we are in terms of the life cycle of this project. So we're kind of in an early work stage. As I mentioned at the beginning of the slide, we had a regulatory deadline of 2030. After extensive early and conceptual work, we've realized we're not going to be able to meet that deadline. Our current target is 2035 to complete construction. And because we have this 5-year gap between our regulatory deadline and when we're planning to do work, it's influenced our strategy and how we actually implement our design phases. And one of that is to advance our geotechnical design before we've actually advanced a lot of the design of the plant. So we've gone through and done some geotechnical investigation, which Orang will speak to, and we're also doing some design of our ground improvement techniques and how we're going to shore up the site for seismic resilience well in advance of the plant design occurring, so we can get to start some of those activities, preload and ground improvement techniques, well in advance of when we otherwise would be able to do it. We're looking to accelerate by a couple of years in doing that, so that would have put us in 2037. So now we're kind of in that 2035 range with that approach. So that's why when we look at our schedule here, we've got some early works packages, and then the design release, that second column really speaks to the design of the treatment plant and the structures that are going on it. And then the heavy construction for the treatment plant is going to start kind of later 2028, 2029. So interesting piece. And then we're planning to do ecological restoration and parks upgrades throughout the duration of our construction. With that, I'm going to pass it off to Randy. He's going to talk to more of the topical pieces to this audience. So.
Thanks, Daniel. Let's look at some things under the ground now. We have carried out a field investigation at the plant site and at the river from both sides, Fraser River and also the McDonald's Slough. This information is like in addition to whatever we had information available at the site. So this is a supplementary investigation. So we had 21 mud rotary holes varying from depths from 40 to 80 meter, 4 sonic holes varying from like 70 to 170 meter depth, and 28 seismic CPTs from 45 to 120 meter. Also, we have carried out downhole shear wave velocity measurements at 3 locations. This at the sonic hole locations up to 120 meter depth. We suspect artesian conditions, and then we install vibrating wire piezometers at the two locations. In addition to this intrusive test, we also carried out the geophysics survey to collect the shear wave velocity measurements across the site within the proposed plant area location. And also from the collected samples, we have carried out regular index test, consolidation test, cyclic simple shear, and direct cyclic simple shear tests. So these are 2 cross sections we are showing here. Let me turn on. So the one on the top is on the north-south direction. So this is the plant area. So, and one at the bottom is at the east-west direction. The plant area is from here to here. So generally at the site, we had fill material and overbank silt underlain by Fraser River sand, which is liquefiable, and then underlying by the marine deposits, clay and silt, which is compressible, and also there's a potential for cyclic softening at the top part of the marine clay. So with this one, so we have challenges of compressible clay and the potential cyclic softening with the clay will undergo, and also the liquefiable Fraser River sand, and underlying by Pleistocene deposit, which is marked in this yellow and this blue color, Pleistocene deposits. We encounter around 40 to 60 meter depth within the plant area, which we didn't expect it at when we went and started drilling at the site. We were expecting it to be deeper because the same Pleistocene deposits are around 130 meter depth within the existing plant area in this area. So the Pleistocene deposits dipping down in the direction of south, and also it's dipping down in the direction of east within this proposed plant area. So key findings, I might have summarized some of them before in the previous slide. So the depth of the Pleistocene deposits are from 40 to 65 meter, but within the existing plant area, we had identified them at 130 meters. So it's a big transition or dipping down in the directions, in different directions. And the Fraser River sand which is liquefiable. And then we also encounter artesian conditions within the marine clay underlying the Fraser River sand. Top part of the marine clay we identified would experience cyclic softening under the design ground motions. Marine clay is compressible, that is subject to long-term consolidation settlement following placement of site-grade fill and also the structural loading. As an example here, some part of the existing plant settled about 900 millimeter, and the site is still settling at a rate of 10 millimeter per year. So what are the proposed mitigation plans? We were thinking about, because what are the problems we have is the liquefaction. 3 problems we have: liquefaction, cyclic softening, and the compressible marine clays. So for the liquefaction purposes, we have proposed to improve the ground with stone column vibro replacement, using stone column vibro replacement technique. So approximately we need about 24,000 stone columns at a reasonable center-to-center spacing, equilateral, triangular pattern. And in order to reduce the post-construction settlement, the preloading, we were proposing the preloading, we need about 2.1 million cubic meter of material needed to preload the entire site. Preloading height varies from the conceptual design stage. It varies from 13 to 17 meter high. And the buildings are almost closer at the boundary of the property. So preloading them at the boundary, you probably need a vertical or near vertical face of the wall. And also the CSM panels proposed at the edge or at the boundary of the site to prevent the lateral movement due to cyclic softening and so on. So the challenges faced in implementing the mitigation measures. First one is vibro replacement stone column. So the Fraser River sand liquefiable, we identified like 2 distinguished layers. Top is like a 15% average fines content, and below layer is like a 5% average fines content. We identify that the 5% average fines content Fraser River sand is more cleaner. There's no interlay of materials, so it's relatively easy to ground improve using the vibro replacement technique. But the top Fraser River sand, which has about 15% fines content, which has interlayer of soil, it'll be challenging to do the ground improvement using vibro replacement technique. So we looked at 2 different sites. We have implemented the ground improvement using vibro replacement. One is at Northwest Langley Wastewater Treatment Plant. Another one is at the Tilbury LNG site. Northwest Langley, the reason we picked these 2 sites, they also have these top layers with 15 to 20% fines. And also they have the layers are interlaid with a clay silt material. So the Northwest Langley one, it was improved with 2.65 meter center-to-center spacing. Only the primary columns only, that means equilateral triangular pattern columns only. And this the ground improvement we achieved in this area is about 1.5 of the previous or pre-improvement strength of the material, or the QC value. We have able to push it 1.5 times higher after the ground improvement. We also look at the Tilbury one, where the pre-improvement values got pushed by 2.0 times the previous pre-improvement value. So where the center-to-center spacing at the Tilbury site is 2.5 meter, little tighter packing compared to Northwest Langley. And this is also, we are just comparing the primary columns only. There's no secondary columns at this stage. So when we look at the data from Iona Island, because we already say that there are two distinguished layers. Second layer has 5% fines content that we think it's easy to improve, compared to the top one, which has 15% fines content and also have a lot of interlayer in it. So we are looking at the top layer now. We are targeting for 15% fines content. That is our target specification there. So that 15% fines content line is shown in this dashed line here. So this black continuous line is the average of pre-improvement CPTs, tip resistant. So what if we push it by two times, similar to what we have it at Tilbury, but we didn't achieve that at Northwest Langley. Still it's below 15% fines content. So it's going to be a lot of challenge there to reach the target specification there. It is reaching at the bottom, but not that. So two aspects. One is facilities may need to be designed with potential liquefaction within the upper Fraser River and liquefying, or additional ground improvement measures needed to push this beyond that 15% target line. So the challenges with the CSM panel, because of the top part of the marine deposit is going through cyclic softening. So once it's softened, your CSM panel, it's better to key in into a non-softened material or it's little harder material, so it will get key in. So installing CSM panels to deeper depth is challenging due to equipment limitations. And then the field trial, as Daniel mentioned, this is a Metro Vancouver preparing an early work packages like a field trial using both stone column installations and also some CSM works to identify what are the limitations at the field and also whether we can achieve really what we are targeting for, or otherwise we may have to do some additional design or structural or accept it is going to liquefy and structurally strengthen our design. So the field trial, it has some practical limitation, but doing the field trial, we will able to reduce the uncertainties around whether we can achieve it, what is the spacing, and whether do we need secondary columns to improve further or mitigate the liquefaction. Or as far as for the CSM panels, we can check the constructability, strength, and also the cement content in addition to laboratory tests and so on. But the limitations of doing the field trial early, and if the contractors, for some reason, if you don't have the same contractor doing the production and the field trial, then we are again introducing the uncertainties in the method. So there is a limitations in doing the field trial as well. So the next one is the preloading. So first of all, it's sourcing 2.1 million cubic feet of material to do the preloading is a challenging. And also it's almost impossible to preload the entire site at once. So because of the site activities and other limitations, so we may have to do better staging of where we are going to relocate the material, and then what we are going to do the work, ground improvement work so the staging is very important, construction staging. And also the buildings are very closer to the property boundary. So the preloading needed almost near vertical wall, which is challenging to make, and we are looking at some options about using like MSC type of wall and everything. We also looked at block wall, but for this height, it may cause some safety concerns and so on. So we are looking at those, how to overcome that challenge. And thank you all for your attention. And yeah. Sorry, the grade raise?
Yeah, you're raising grade 3 meters, correct?
Correct.
Yeah, correct.
Are you going to reinforce that 3 meters with geograde?
Something we haven't looked at yet. I think one of the complexities about our plant is the foundations of our structures are quite deep. So our existing grade's around 2 meters. The shallowest foundation is -1, and then we're lifting grade around that up to another 3 meters. So they're quite deep structures. So I think it's as we fill the material around the structures we're building is when we'll have to look at those stability options. Good question. Yep.
Yeah.
Yeah, I was wondering, as an alternative for the preloading, because I see it's quite high, did you consider, or why not consider this vacuum consolidation, for example?
We are looking at that option as well, the vacuum consolidation, but we don't have an answer yet for whether probably one of the trial we need to do it.
Could make sense.
Yes.
Yeah, for this type of preloading, did you check that to do it in stages to ensure that you are not exceeding the shear strength of the soils?
Yes, it's a good question. If you don't want to create a local failure there, yes. So we check that one, whether the soil will take, but the idea is we are not going to put that entire load at once.
Okay. So there's staging and
Staging, yes.
Yeah, usually when we stage it, we every time we do thick testing to ensure that
we need to measure the flow pressure dissipations and everything, which is important because you don't want that the flow pressure generate all the way and put next load and cause a localized failure on that front. So we'll be instrumenting it.
you have time for one more question.
Was there an objection to installing piles, ideally with vibratory pile drivers? I know it's really have to be long, but it's certainly not understood that.
Yeah, it's part of our indicative design was a combination of the stone columns and piles. The way we separated the contract was we put the pile design with the actual foundation of the treatment plant. So that's most likely will be a combination of both. So when we talk about some of the limitations of our ground improvements methods, some of those limitations might get taken up by the pile design and the foundations.
Thank you very much for that.
I just one more plug out there. If anyone has sand, I am looking for it.
Thank you very much. In the interest of time, I'm sure you can find both of you guys later. Thank you all. So we'll have a quick coffee break. If we can reconvene here about 3:40, that would be great.